Everyone knows that good behaviour is rewarded with gifts at this time of year. But how do you know if your shader programs are behaving well? If they are maths heavy, texture heavy, or prevent the GPU from applying optimizations, you could see performance problems on mobile. Here are some tips for reducing shader cost. Although we always want to produce the highest quality graphics, it's important that we assess the on-screen impact and make a trade-off between quality and efficiency. Ideally, you should use medium precision for your shader variables everywhere that high precision is not required. This reduces energy consumption, reduces register pressure, and can make things run faster. In most cases, using medium P for colour computation will cause no noticeable impact on the visual output. If your shader program contains computation that depends only on literal constants or uniform values, it produces the same result for every thread in a draw call or compute dispatch. The Mali driver can optimize this away, but it still has a small cost. Where possible, you should move this kind of computation into application logic on the CPU. Shaders that have side effects that are visible in memory outside of the fixed graphics pipeline can disable many GPU hardware optimizations, such as the use of early ZS testing and hidden surface removal. Shader side effects can be caused by writes into shader storage buffers, stores into images, or use of atomics. You should aim to minimize their use. A fragment coverage mask determines which sample points in each pixel are covered by a fragment. This coverage information determines which samples in the frame buffer get updated. Ideally, the coverage mask is known before fragment shading, as this allows an early depth update, but some fragment shaders can change their own coverage mask, for example by using a discard statement or using alpha to coverage. Shaders with modifiable coverage must use a late ZS update, which can reduce efficiency of early ZS testing and fragment scheduling for later fragments at the same coordinate. Similarly, if fragment shaders write to GL frag depth, the depth value cannot be known early, and the fragment will be forced to late ZS test and update. Transparent fragments cannot be used as occluders during hidden surface removal. This puts more pressure on the GPU to process content that might not end up on screen. The common cause of transparency is the use of API-enabled blending that uses the destination colour as an input. However, fragment shaders that read programmatically from the colour buffer, for example by reading from GL last frag colour arm, or from an earlier Vulkan subpass, are also effectively transparent and cannot be a hidden surface occluder. Mali Offline Compiler, available with ARM Mobile Studio, enables you to analyse your shader programs on any of the available Mali GPUs. It provides a cycle cost breakdown for the shader's arithmetic, load store, varying and texture usage. You can check the percentage of arithmetic operations that are performed at 16-bit precision or lower, and you can see information about the shader's use of language features that can impact the performance of shader execution. Mali Offline Compiler is free to use as part of ARM Mobile Studio. Download it today. Once you've found out whether your shaders are naughty or nice, you can relax and enjoy a great festive holiday. Thanks for watching.